everybody. Here we are. We are going to start today talking about polar integration. This is section 15.3 of the textbook. I guess this talk is two parts, and then a sort of third part we're going to talk about doing this in 3D with what's called cylindrical coordinates, but let's not get ahead of ourselves there. We'll start here and we'll make it there. All right. So let's recall polar coordinates. I know you've seen these before in maybe pre-calculus and probably pre-calculus, and I know calculus 2 as well. So let's see, what are these polar coordinates for the plane? So let's say we have a point P in the xy plane, and we're going to give it polar coordinates, r and theta. What is the meaning of r and theta? Well, let's see. Let's join our point P to the origin with a line segment that we're going to name L, but that's fine. It's got length r, and its angle counterclockwise from the positive x-axis is theta. So that will be the definition of r and theta. R gets this is kind of like this radius, right? This length of, this radius of like a circle that's centered at the origin, say, containing this point P. And theta tells us how far we travel along that circle, kind of angle-wise. So, you probably, if you remember polar coordinates from the past, you remember that they described circles pretty nicely. So let's get there. All right, and then just some conventions of sort. So we'll assume here that our radii are bigger than or equal to 0. It's possible you can let them be less than 0. That's totally fine. But I don't think we're really going to need it that much. So it's just for purposes of making these a little bit more unique, then we'll assume that r is bigger than or equal to 0. And we could let theta be negative, in which case we'd count the angle going clockwise. Negative radius means we'd count going sort of backwards along the negative x-axis there. That's fine. So I think you can get to a point in the plane via polar coordinates by walking out along the x-axis a distance of r and then turning an angle of theta in the counterclockwise direction. Oops. Okay, so how do we relate these polar coordinates to xy coordinates, the ordinary rectangular ones? Well, we'll use some right triangle trig, right? So we have this picture here where our point P is given in polar coordinates by r theta and in standard rectangular coordinates by just say x and y. Then here we have this right triangle, and it looks like cosine of theta is x divided by r, and sine of theta is y divided by r. So we can solve for x and y, and we get x is r cosine theta, y is r sine of theta. Okay, and I think you probably remember this from the past. If you remember anything about polar coordinates, you probably remember these relationships. And then one other one that comes to us from Mr. Pythagoras, which is that x squared plus y squared equals to r squared, right? So we'll probably be making use of these as we go about our day using polar coordinates to do double integrals. So let's first, though, before we do any integrals, let's remember why we might even want these polar coordinates to begin with. The idea is that we were going to try to do integrals over regions of the plane that are not very nicely described using rectangular coordinates, but are nicely described using polar coordinates. So let's think first about some polar equations where we have one variable, either r or theta, equals to a constant. So let's C be a constant. Then what does a polar equation of the form r equals to c yield? It yields a circle in the plane that is centered at the origin and has radius c. So we'll see a picture of that in a second. Let's also think about a polar equation of the form theta equals to c. This is like saying all the points that you get from moving an angle of theta from the positive x-axis. Well, this will give you a line in the plane. It maybe only would give you a line segment or a ray, I guess, if you let theta be only bigger than or equal to 0. But if you also let r be bigger than or equal to 0, then you'll just get a ray. But if you let r be also less than 0, then you'll get back the whole line. So let's see a picture of these guys. So here we have the equation r equals to 1. Oh, okay, that's a circle of radius 1 in the xy plane, right? It's centered at the origin, too. This is a good old unit circle. We remember this one, right? And what is the equation in rectangular coordinates for that, but rather x squared plus y squared equals to 1. So you might sit there and ask yourself, which of these is a sort of simpler equation to deal with? I think it's probably this polar one, r equals to 1. So this will be kind of the utility of polar coordinates, is that circular type things are much more simply described in polar coordinates than they are in rectangular coordinates. Okay, likewise here we have this line, theta equals to pi over 4. That means we have this constant angle of pi over 4. And as I was saying before, when I was kind of botching what I was saying, if we just let r be bigger than or equal to 0, then we just get this ray kind of on the top right part. If we also let r be less than 0, then we get this bottom half of the line as well. And so I don't know. I mean, you can sit here and wonder, is, theta equals pi over 4? It's probably a little bit simpler than y equals x, but I think for some reason, we're probably not going to need to worry about this as much as we're going to like things like this, that r equals 1 is much simpler than x squared plus y squared equals 1. Whereas theta equals pi over 4 is maybe only a little bit simpler than y equals x. We were good enough with that description before. Okay. So now that we have some good polar equations, let's wonder about some polar regions of the xy plane, namely some polar boxes. And right, we'll put this in quotations, right? What do we mean by a box? It's been a minute since we've talked, so let's remind ourselves of what we mean by that. So in the xy plane, we're going to call something a box if it's a region that can be modeled with bounds that are all constant values. So when we were doing rectangular coordinates, right, the only boxes we had were rectangles, where x varied between a and b and y varied between c and d. So now we're going to do the same thing, except instead of xy coordinates, we're going to use these polar coordinates r theta. So let's let c, d, alpha, and beta be some constant values that are going to give us the bounds for, this sort of integral that we're going to set up eventually. So we'll call the polar box B to be the set of points in the plane r theta, such that r varies between c and d, and theta varies between alpha and beta. Now, generally, this gives us something called a sector of an annulus, and I'll show you a picture soon. And we get a whole annulus if theta goes all the way around the circle from 0 to 2 pi. So let's see some pictures. Here is a sector of an annulus. It's kind of just like a sector of a circle, but thicker, right? We have this thickness to it. So we can see here we have r goes between 1 and 2, right? We have inside we have a circle of radius 1, and outside we have this arc of a circle of radius 2. And theta goes between pi over 4 and pi over 2. See, here's theta equals pi over 4, that line that we saw earlier. And theta equals to pi over 2 is this line there, right? So that is a sector of an annulus. That's pretty fun. Let's see. I think the next picture is probably a whole annulus. Ah, yes, it is. Okay, so it's the same radii, 1 and 2, but now we'll let theta vary from 0 all the way around to 2 pi. So this is what's called an annulus. Okay, so I don't know. If you want to impress your friends and scare your enemies, you can say that word, annulus. Okay, so one extra thing I like, these are probably our two main types of polar box, although they're kind of just the same thing, where the only difference is in the thetas. There's two other kind of types, though. What if we let this lower bound for the radius, what if we let this number c be equal to 0? Then we'd stretch all the way back to the origin here, right? And we'd have all this empty space here would all be filled in. So we'd go all the way back. That would give us either like a disk on this side or a sector of a disk on that side. So those are some other kind of polar boxes that are actually pretty common regions of integration in this course. So we might like having those around too. Okay, so if we're going to do some integrals using polar coordinates, remember that this polar coordinate transformation is going to do some kind of warping of area. If we're looking at the sort of plane whose x and y axes are labeled by r and theta in the ordinary xy plane, then there's going to be some kind of warping between that r theta plane and the xy plane. And we need to account for that when we take any kind of integral. So we have our coordinate transformation here. X is r cosine theta, y is r sine theta, and we can get from that what's called the Jacobian matrix, right? If you were around for the lecture on section 15.9, then you probably remember this guy, or maybe you don't. It's been a really long time since then. Anyway, what is this Jacobian matrix? Its entries are the derivatives of x and y with respect to r and with respect to theta. So in the first column, we have derivatives of x and y with respect to r. That gives us cosine theta for this guy and sine theta for that guy. In the second column, we have the derivatives of x and y with respect to theta. So that gives us minus r sine theta in this entry and r cosine theta corresponding to this one in this place. Okay, and so now that we have that matrix, what are we going to do with that? Well, we would like to get just one value out of it, so we'll take its determinant. And I think if you were present for the lecture on section 15.9 right before spring break, then I think we actually did this example, so this might be redundant right now. So what is the determinant of this matrix? Well, we get here cosine theta times r cosine theta is r cosine squared theta. Then we subtract minus r sine theta times sine theta. That gives us plus r sine squared theta. And you can factor out r. You get r times cosine squared theta plus sine squared theta. Oh, but cosine squared theta plus sine squared theta is 1. So we just get here that this determinant is r. And what good is having that determinant again? Like, what are we supposed to do with that? Oh, right. So anytime we do an integral and we transfer to polar coordinates to do our integral, then we need to multiply our integrand by this Jacobian determinant, r. So, oh, right. And of course, I always forget this one. It's the absolute value of this Jacobian determinant that we need to multiply by. But we are going to assume that r is always bigger than or equal to 0. So this absolute value is really just r itself. So let's integrate over a polar box. So here's the formula in case you're forgetting. So let B be our polar box. So either an annulus or a disk or a sector thereof of one of those things. And let's let f of xy be some function that's defined over that polar box. Then what is the formula again? Well, if we want to integrate over this polar box, the function f of xy, we will form this, what do they call it? Iterated double integral, right? Where we'll do the theta integral last. That's just kind of a convention. It's not absolutely necessary in this case because Fubini's theorem still will hold over a polar box. That's fine. So we'll have the integral from alpha to beta of the integral from c to d of now instead of f of xy, we'll replace x with r cosine theta and y with r sine theta. And then right here is that Jacobian determinant r that we have to multiply by to sort of keep track of how our coordinate transformation from the r theta plane to the xy plane is going to do some kind of warping of areas. So we'll keep this here. So let's see. All right, so I guess it's time for an example now that we have the formula at hand. So let's let B be the polar box where the radius r goes between 0 and the square root of 3. And the angles theta go between 0 and pi over 2. This shape is a quarter disk of radius the square root of 3. I think you might remember this. I believe it was in written homework 6, I want to say, is that you integrated some function over this quarter disk, but you used rectangular coordinates, or at least you were supposed to. And that was doable then, but now let's do that same written homework, but in this time let's use polar coordinates instead, because this is a polar box, so it should be doable by polar coordinates. So I don't know, in case you're forgetting, here's a picture of that polar box. This is the radius square root of 3, and we just go from 0 to pi over 2, so we just trace out that quarter in the first quadrant there. So I think the function that we integrated in written homework 6 was f of xy equals to x times y. So let's repeat that one there. And we'll use the formula from the previous page. So we'll have the integral from 0 to pi over 2 of the integral from 0 to the square root of 3 of now xy becomes r cosine theta times r sine theta. And oh, don't forget this Jacobian determinant, r. Okay, and let's see. So we can clean this up here. We get r cubed times cosine theta times sine of theta. So we'll integrate that first with respect to r and then with respect to theta. So let's watch it go. Let's see. The integral with respect to r will give us r to the fourth over 4, which we will evaluate at r equals the square root of 3 and r equals 0 and take the difference. And then we'll come back and after the fact, we'll integrate cosine of theta times sine of theta with respect to theta. But let's see, what do we get here? The square root of 3 to the fourth is 9, and 0 to the fourth is 0. So we just get 9/4, which we can now yank outside the integral. So we have 9/4 times the integral from 0 to pi over 2 of cosine of theta times sine of theta d theta. Let's see, how can you do that integral? Oh, I know, u substitution, right? So let's see, I'll let u be equal to sine of theta. That's easier to do. There's no minus signs this way. Then du is cosine of theta d theta. And let's change the bounds. If we're going to let u be sine of theta, then when theta is 0, we really have u of 0 equal to, oh, also 0. But then when theta is pi over 2, u of pi over 2, that should be sine of pi over 2. Oh, that's 1, right? So now we'll integrate instead with respect to u. We'll have 9/4 times the integral from 0 to 1 of u du. And this gives us 9/4 times u squared over 2, which we'll evaluate at u equals 1 and u equals 0 and take the difference. And that gives us, let's see, we get 9/4 times 1/2, which is 9/8. And I think if you did that written homework 6, you might recognize that this was the answer then using rectangular coordinates. So that's nice to see, sort of sanity check that doing this with a different coordinate in a different coordinate system gives us the same numeric answer at the end, which it should. Great. Okay, so let's see. Let's do one more. So this one asks us to compute the volume of the region that lies above the disk x squared plus y squared is less than or equal to 1 in the xy plane, and below the plane 2x plus y plus z equals to 6. So this is a region in space, but let's think back and remember now. Remember that double integrals do, in a sense, compute a volume of sorts, right? The region of integration that we use to set up our bounds, that's the sort of base of our solid, and the function that we integrate, its graph in space over that region of integration, that gives us the sort of height. So we have the base being the region of integration in the xy plane, and the height being governed by this sort of graph of this function. And so the integral then of, say, f of xy is actually the volume of the solid between that region of integration in the xy plane and the graph of the function in question. So let's see, if we are going to compute a volume this way, then we are going to use a double integral. But what is the function that we're going to integrate? Perhaps you can think about that for a second. I'll let you think about that for a second. Is there any function of the form, say, z equals to f of xy in any of this information? I think that there is. I think that if we take this plane here and solve for z, we get something like z equals to 6 minus 2x minus y. Now, maybe we'd like to get like a better handle on what this thing is that we're trying to compute the volume of and how we might set up this integral. So the best thing that you can do, especially now that we're doing like everything online, is to go to GeoGebra. So I'm going to go ahead and do that here. So here we have GeoGebra, the 3D calculator. Love this thing, right? And so You might notice here the red, I think, is the x-axis, the green is the y-axis, and the blue is the z-axis. And don't ask me how I know that. I must have tested it out sometime. Anyway, let's graph first that sort of baseline region of integration. Now, it says it's the disk x squared plus y squared is less than or equal to 1. I'm just going to actually graph just like the sort of cylindrical boundary of that in all of space. So I'm just going to graph this guy that says x squared plus y squared equals to 1. This gives us this kind of cylinder, right, in space. And it comes about from, the ordinary unit circle in the xy plane just extended upwards indefinitely. Okay. And then also, let's graph that other thing. We had what? Z equals to 6 minus 2x minus y. Okay. That's this plane. Oh. Sorry, GeoGebra is going a little slow here. Maybe it's getting a lot of usage now that everyone's working from home. Come on, GeoGebra. Why you gotta do this? Okay. We'll just leave it at that. So you can see here this region that we're trying to find the volume of has got this kind of cylindrical part, but then it's kind of cut off by this plane that cuts through. And so the region of integration, I think we can take as just this disk, x squared plus y squared is less than or equal to 1 in the xy plane. And the function that will integrate is this z equals 6 minus 2x minus y. So, okay. So let's go back to the slideshow here and gather our thoughts before we do this integral. So we're going to integrate the function f of xy equals to 6 minus 2x minus y over the unit disk in the xy plane. But note that unit disk is a polar box, right? It's the set of r theta such that r goes between 0 and 1, and theta goes all the way around from 0 to 2 pi. So that's good. So a couple of things to remember here is, like we were saying, double integrals do generally compute volumes between the xy plane and the graph of some function in space. And another thing to remember is that GeoGebra 3D Calculator is your friend when it's not lagging. Okay, so noted. Anyway, let's do this integral. So, oh gosh, sorry. So we'll just go one step at a time now. So our region of integration was what? Theta went between 0 and 2 pi, and r goes between 0 and 1. And then our function is 6 minus 2x minus y. Well, 2x becomes 2 times r cosine theta, and y becomes r sine theta. And then don't forget to multiply your entire integrand by that Jacobian determinant for polar coordinates, r, right? And you multiply the whole integrand, so every single term gets multiplied through by r. So I'm going to do that in this next step. So the thing we'll integrate is 6r minus 2r squared cosine theta minus r squared sine theta. Okay, well, we can do that integral with respect to r. That's the first one here, right? And let's see. So 6r becomes then 3r squared. 2r squared cosine theta becomes 2/3 r cubed cosine theta. And r squared sine theta becomes 1/3 r cubed sine theta. And so now we'll evaluate this guy at r equals 1 and r equals 0 and take the difference. So we get 3 minus 2/3 cosine theta minus 1/3 sine theta. Now we'll integrate this guy with respect to theta from 0 to 2 pi. So let's see, we get something like 3 theta minus 2/3 sine theta, then plus 1/3 cosine theta. And we'll evaluate this expression at theta equals 2 pi and theta equals 0 and take the difference. So let's see, 3 theta evaluated at 2 pi gives us 6 theta. Luckily, sine of 2 pi is 0, so that term disappears. And cosine of 2 pi is 1, so 1/3 cosine of theta becomes then 1/3 there. And now let's evaluate everything at 0. We get that 3 times 0 is, 0. And sine of 0 is also 0. And cosine of 0 is 1, so 1/3 cosine of 0 becomes just 1/3. And so now let's subtract these two. We have 6 pi plus 1/3 minus 1/3 leaves us with just 6 pi. All right, so that was fun. Next on the agenda will be to integrate over some polar non-boxes. So join us in part 2 of the video, and we will look at some polar non-boxes and do some fun integrals over them. Alrighty.